The topic today is seismic detailing of special shear walls and coupling beams. Special shear walls, by now you know, means specially detailed, the only kind that you are allowed to use in buildings that are assigned to seismic design category D. The first few slides will be the same as what you saw on Wednesday when we discussed frame detailing, because the the both are taken from the same source, and you will see in a minute that the materials restrictions apply to both. In any case, let me get started with a few slides from Wednesday. The design that we will discuss is based on BNBC 2020, which has been recently gazetted, as you know, and the reinforced concrete design and construction provisions of BNBC 2020 are based on those of ACI 31808. That is obviously important, and I might have mentioned earlier, I don't remember, ACI 31808 comes with a commentary under the same covers. The provisions are in the left-hand column on every page. The commentary is on the right-hand columns. The commentary is extremely valuable, which you do not have with the BNBC. The commentary is not available to you in that document. So if you know if you want to find out the background on a BNBC provision, if you know the corresponding section number in ACI 318, and that can be figured out without a lot of problems, then you have access to the commentary that may give you very useful background and so forth. Okay. So the fact that it is ACI 31808 is something you need to know. And as I mentioned the last time, since ACI 31808, there have been 3 editions of ACI 318, 31811, 31814, and 31819. The document underwent a complete reorganization in 31814, which means, among other things, that beyond Chapter 3, nothing is where it used to be. Everything has been moved around. And pretty much with the exception of the seismic chapter, which remains intact, it has not been split up and placed in different places as other chapters have been. But what used to be chapter 21 became chapter 18 in ACI 31814. And today I mention it specifically because as far as shear wall, special shear wall detailing is concerned, very major changes were made in 31814 directly in response to the Chile earthquake of 2011. And today I will go into those changes, tell you about them, because those are very major, and I thought that you at least need to know about them. Further changes have been made, very significant changes in 31819, which I will not go into. The 31819 changes are somewhat controversial. They are not in use even in the United States yet, because code adoption takes some time. So that will be left for a subsequent occasion. But the 31814 changes today this is the only time in the entire series that I will bring up 3.18.14 changes for discussion. As pointed out the last time, the seismic design provisions in 3.18.08 are in chapter 21 of the document. In BNBC 2020, I didn't notice this, I don't know. In BNBC 2020, part 6 is structural design, as you know, a huge part of the code. In that part, chapter 8 is on detailing of reinforcement in concrete structures. Section 8.3 is where you go for seismic detailing, earthquake-resistant design provisions. Chapter 6 of part 6 is on strength design of reinforced concrete structures. And as I mentioned previously, that remains applicable. The provisions of chapter 6 remain applicable unless specifically modified by section 8.3. And there are cases where chapter 6 provisions have been modified by section 8.3. I do not believe in shear wall detailing you will come across it. No, actually, I take that back. Anyway, okay. So the chapter 6 provisions remain applicable unless specifically modified by section 8.3. All section numbers not in blue are 3.18.08 section numbers. The section numbers in blue are BNBC 2020 part 6 section numbers, chapter 6 or chapter 8, and the 3.18.14 section numbers when I go into 3.18.14 are in green. So that makes it easier for you to know where things are from. Yeah. Some basic stuff that I have gone over with you probably more than once. Seismic design, in its very essence, is an exercise in trade-off between strength and inelastic deformability. The higher the inelastic deformability, the lower the need for strength, and the lower the inelastic deformability, the higher the need for strength. Inelastic deformability is the ability of a structure to continue to carry full factor gravity loads as it deforms beyond the stage of elastic response. And elastic, as I mentioned, it does not necessarily mean stress proportional to strain. It means no residual displacement. The earthquake passes, you get your structure back intact and very importantly located where it used to be before the earthquake. Inelastic deformability comes from proper detailing of the structural members and the joints. This is why we are spending so much time on the detailing requirements of ACI 318 BNBC 2020. Part 6, section 2.5 sets the design force level or the strength that we are designing for the strength level. Detailing rules are given in the materials chapters. So it is part 2, chapter 8 for, these are all part 6, I believe. I didn't notice that either. Anyway, let's talk about, part 6, chapter 8 for concrete. Part 6, Chapter 7 for masonry, Part 6, Chapter 10 for steel, and Part 6, Chapter 11 for wood. Okay, so that's where the detailing requirements are for the various materials, and those chapters reference material standards. This Part 6, Chapter 8 and Part 6, Chapter 6 reference ACI 31808. Okay, so for concrete, the reference is definitely ACI 31808. As also mentioned previously, 3 levels of detailing are defined in our codes and standards, including ACI 318. Ordinary detailing, intermediate detailing, special detailing. Special detailing gives you high inelastic deformability. Intermediate detailing gives you lower inelastic deformability, and ordinary detailing gives you even lower inelastic deformability than does intermediate detailing. R value, the R that is in the denominator of the design base shear equation, provides the link between design force level and the level of detailing. If the R value is high, the design force level is low, and you need probably special detailing. And if the R value is low, the design force level is high, and then you probably can do with ordinary detailing. If your design category is A, which will not be the case in Bangladesh, you don't have design category A, no seismic design is required. So you are not in that situation. Design category B, unrestricted trade-off between strength and inelastic deformability, unrestricted. Design category C, trade-off is not unrestricted anymore. Intermediate detailing is required as a minimum. And if your design category is D, then it is not unrestricted at all. You have to provide special detailing as the minimum level of detailing. Now, when it comes to shear walls, as I pointed out, shear walls can be used as or in bearing wall systems, in building frame systems, in dual systems. And dual systems may be with intermediate moment frames or special moment frames. The R values and also C sub D and omega sub 0 for these systems are to be found in table 12.2-1 of AC7, and there is a corresponding table number in BNBC 2020. I didn't go into table numbers here, okay, but we have discussed them. Okay, if the shear wall that we are designing is part of a bearing wall system, then if it is special reinforced concrete shear wall, R value is 5. If it is ordinary reinforced concrete shear wall, R value is 4. If the shear wall is part of a building frame system, then for special shear walls, R is 6. For ordinary shear walls, R is 5. If shear wall is part of a dual system featuring special moment frames, then for special shear walls, R value is 7. That is the highest we can get with a shear wall system. And for ordinary reinforced concrete shear walls, the R is 6. If our shear wall is used as part of a dual system that features intermediate moment frames, then for special shear walls, we get 6.5. And for ordinary shear walls, we get 5.5. So in any case, the point is that the R value comes from the table in ASC 7 that gives us design parameters and also height limits. Okay, So the only shear wall system that does not have height limit on it is the dual system with special moment frames. Every other case you will see, particularly in high seismic design categories, we have height limits. Okay. The materials restrictions, these are in common with special moment frames. So all the restrictions that we discussed earlier as being applicable to special moment frames also apply to special shear walls. So we have gone over these restrictions. I still included them in this slide set so that you have a complete slide set for shear walls, but I will go over them kind of quickly. Okay, so normal weight concrete, no upper limit on the compressive strength, but the compressive strength cannot be any lower than 21 MPa, 3,000 pounds, 3,000 psi, 3 ksi. Okay, lightweight concrete, we now have an upper limit which is 35 MPa, 5 ksi. And that upper limit, as I mentioned, is because we do not have sufficient test results demonstrating that the hysteretic load deflection behavior of lightweight concrete members are comparable to those of very similar normal weight concrete members. As more test results become available, that limit may very well be relaxed, although the limit has held now for quite some time. There was a change, but that was several editions ago. The limit used to be 4,000 psi. The reinforcement, the preferred type is the weldable A706, which until recently came only in grade 60 or in MPa grade 420. You are, however, allowed the normal billet steel A615, grade 40 and 60 in MPa 275 and 420. In Bangladesh, most of the reinforcement is BDS ISO 6935-2, which comes in grades 300, 350, 400, 420. The higher grade that is in use cannot be used. The higher grade of reinforcement that is in use in the country cannot be used as part of the seismic force resisting system in design category D. I spent quite a bit of time, I think, in the first concrete course where we went into material specifications. ASTM A615 grade 275 and 420, as I mentioned, is allowed, but in both for A615 reinforcement and for the BDS 6935-2 reinforcement, we have supplementary requirements which are not part of the ASTM specification or the BDS specification. So these are requirements in BNBC that are in addition to those in the material specifications. The first of those restrictions is that the actual yield strength shall not exceed the specified yield strength by more than 125 Newton per square millimeter upon retest. So this is in our units 18 ksi. So the actual yield strength cannot exceed the specified yield strength by more than 18 ksi. Upon retest, you can go another 3 ksi, but that is the absolute limit. You cannot go beyond 21 ksi overstrength. This is extremely important because if the yield strength of the reinforcement is much higher than specified, the flexural strength of your member that is reinforced with that steel will be significantly higher than what you intended. That high strength member will attract more shear force to itself in an earthquake situation. We will not be correspondingly increasing the shear strength, making brittle shear failure more likely. Okay? So this is an exceedingly important restriction. The second restriction, which is part of BNBC 2020 but did not come to ACI 318 until the 2014 edition, says that the elongation of a reinforcing bar over an 8-inch gauge length. So the deformation of an ASTM A615 or BDS 6935-2 reinforcing bar over an 8-inch gauge length shall be the same as that of the same bar that complies with ASTM A706. So there shall be no difference in deformability. That is, there shall be no difference in the deformations over an 8-inch gauge length between A615 or BDS 6935 bars and A706 bars. The third of three supplementary requirements is that the actual tensile strength shall be no lower than 125% of the actual yield strength when tested. And I explained to you why, and I will not go into that a second time. Okay, then the value of F sub YT, this is now yield strength of transverse reinforcement, used to compute the amount of confinement reinforcement. So when transverse reinforcement is used for confinement of the concrete, its strength can be up to 100 KSI, 700 MPa. It shall not exceed 700 MPa. When you use the same reinforcement as shear reinforcement, then you cannot utilize a yield strength of more than 420 MPa, because if you do, you'll be looking at wide shear cracking, which is unsightly and can be dangerous. Okay, so once again, the yield strength of transverse reinforcement in its role as confining reinforcement is restricted to no more than 700 MPa. But when you utilize the same reinforcement in its shear resisting role, the highest F sub YT you can use in computations is 60 KSI. Beyond that, we do not allow in order to avoid wide shear cracking. Okay. Now is material that obviously has not been discussed before. Shear walls, like any other structural member, have to be designed for shear and also for flexure and axial loads. The flexure and axial loads go together, as in the case of a column. We cannot design separately for flexure and for axial load. It's combined flexure and axial load, and the shear design is done separately. Typically, we would do the shear design first in the case of a shear wall, and then go into the flexural design. Okay, so design of special shear walls for shear. The design requirements for special shear walls were changed in significant ways in ACI 31814 in view of lessons learned from the Chile earthquake. I said 2010, it was 2011, it was 2010. Okay. So this is something I mentioned at the outset. So you will see some things in green that on the slides that do not apply to you because you are designing by BNBC 2020, but those things I included for you to know what has already come to ACI 318 and what you can expect in the future. Also, there is something called standard of care. If you know of something, if you know that something better than what is in the code is available out there, the standard of care requires that you use that in your design. I do not want to suggest that you go that far. That is not up to me. But I thought that it is good for you to know because these are truly important changes. Okay, what you do with it is a different story. Okay, as in the design of basically all structural members except beam column joints of special moment frames. In design, we will keep V sub U less than or equal to phi times B sub n, or we will have to provide design shear strength phi times B sub n. B sub n is the nominal shear strength, at least equal to the required shear strength B sub u. Okay? Now, in the case of special moment frame beams and special moment frame columns, we design for the largest shear that can develop in the member. That's our V sub u, not the shear that structural analysis under code prescribed seismic forces tell us develops in the member. Okay? So we design every special moment frame beam and every special moment frame column for the highest shear that can develop in the member. In the case of shear walls, we still do not do that, mainly because we do not quite know how to calculate the largest shear that can develop in a shear wall, even today in 2022. We have a good idea, but we really cannot calculate. So in the case of shear walls, the V sub u comes directly from analysis of the structure containing our shear wall under code prescribed seismic forces. It is not the largest shear that can develop in our shear wall. This is extremely important for you to understand. Okay, the shear, design shear, the required shear strength comes directly from analysis of the structure under code prescribed seismic forces. Knowing that this is not the conservative thing to do, we play with the phi factor. The phi factor for shear design is 0.75. ACI 318 says, and BNBC 2020 also says, if you are designing a shear wall for shear that is likely to fail in shear before it has a chance to fail in flexion. I will repeat. If you are doing the shear design of a shear wall that is likely to fail in shear before it has a chance to fail in flexion, the phi factor for shear design shall be 0.6, not 0.75. Now, I paraphrased. ACI 318 language is if the nominal shear strength is less than the shear corresponding to flexural strength. The problem is that we do not quite know how to calculate the shear corresponding to flexural strength. If we did, we probably would have designed for that. Okay, so the code language is fine. It states the principle, but you still have to figure out when to apply 0.75 and when to apply 0.6. There are a lot of people who design for a fee of 0.6 across the board, but that is not intended by the code, and that in a way would be wasting your client's money when shear failure simply is not a possibility. So roughly speaking, if the height to length ratio, total height to total length ratio of a shear wall is less than 1, it definitely will fail in shear before it has a chance to fail in flexion. Up to 1.5, you have no assurance that it will not fail in shear before it has a chance to fail in flexion. At about a height to length ratio of 2, you can be pretty sure that unless you have done something strange, like forget about putting horizontal shear reinforcement in, your wall will fail in flexure before it has a chance to fail in shear. So walls with a height to length ratio larger than 2 are flexure governed. They will fail in flexure before they have a chance to fail in shear. There is no reason to use a P of 0.6 for those walls. For shorter walls, if you want to be conservative, I would say all the way up to a height to length ratio of 2, use a P factor of 0.6. But beyond that, it is a waste of money to use a P of 0.6. Now, anyway, let me stop there. I could go on that topic, and quite a bit has happened in 2019, but I don't, it may only confuse you. Okay, so the V sub U we talked about, V sub U has to be less than or equal to phi times V sub n. The phi we talked about, V sub n comes partly from concrete, partly from horizontal shear reinforcement. A sub CV is the shear carrying area of the section, shown hatched in the picture. A sub CV is the total length of the shear wall from one extremity to another extremity times the thickness of the web. The flanges, the overhanging flanges don't count. If you have columns at the end, the overhanging portions of the columns don't count. It is the length of the shear wall multiplied by the thickness. Okay, A sub CV. The shear that concrete can carry is in throughout the ACI code, it is concrete is always good for 2 square root of f sub c prime, which should be in your units. 2 would be 0.17 square root of f sub c prime. Now, there were tests of low-rise shear walls at the Portland Cement Association a long time ago. I believe it is before my time. It was in the 70s, early 70s, or I believe early 70s, that showed that concrete in low-rise walls, height to length ratio less than or equal to 1.5, can do better than 2 square root of f sub c prime. So with those test results, we proceeded to complicate the code. So ACI 318 says for walls with height to length ratio of 1.5 or less, the concrete can carry 3 square root of f sub c prime in our units. For walls with height to length ratio larger than or equal to 2, concrete can carry 2 square root of f sub c prime. Between height to length ratios of 1.5 and 2, we interpolate linearly between 3 square root of f sub c prime and 2 square root of f sub c prime. Okay, so that's the concrete resistance part. Now, any part of phi times b sub n that cannot be resisted by the concrete, we have to design horizontal shear reinforcement for. So rho sub t will be calculated based on phi times b sub n minus a sub cv times alpha sub c times square root of f sub c prime. Okay, so rho sub t will depend on how much shear needs to be resisted by the horizontal shear reinforcement. And the total shear that can be imposed cannot exceed 8 square root of f sub c prime. That number of 8 can be 10 under some circumstances. I will let you read the details. But the point is that when shear is very high, if you imagine this white, the white portion of the slide as a shear wall. Imagine this as a shear wall with a point load applied at the top. If the applied load is very high, it will be transferred to the foundation through compression struts that form within the shear wall. And those compression struts will fail in compression at a shear of about 8 square root of f sub c prime. And that number cannot be improved by providing horizontal shear reinforcement because it's compression crushing. This is why we have an upper limit. Okay, so V sub n we have discussed, phi we have discussed, phi times V sub n has to be at least equal to V sub u. The V sub n comes partly from concrete, partly from horizontal shear reinforcement. How much can be carried by concrete we just discussed. So that tells us how to figure out how much horizontal shear reinforcement we need. This is a detail, the ratio, the height to length ratio used for determining V sub n for segments of a wall is the larger of the ratios for the entire wall and the segment of wall considered. That is a detail that I don't know how important it is. Now, the rho sub t, the horizontal shear reinforcement required, you will determine it by calculation, but under no circumstances shall it be any less than 1/4%. Okay, 1/4%, and the spacing shall not exceed 18 inches. So I should have pointed at that. Okay, so the horizontal shear reinforcement, irrespective of how much you need, shall not be any lower than 1/4%, and the spacing shall not exceed, the vertical spacing shall not exceed 18 inches. Many tests have shown, particularly for low-rise shear walls, that the horizontal shear reinforcement will not do you any good unless it is coupled with vertical shear reinforcement. Okay. So we provide not just horizontal shear reinforcement, which is obtained from calculations, but also vertical shear reinforcement to go with it. The vertical shear reinforcement also shall not be any less than 1/4%, and the horizontal spacing of that reinforcement shall not exceed 18 inches. Okay. Typically, in a shear wall, the flexural reinforcement, the reinforcement needed for flexure and axial load, we typically concentrate that near the ends. Not always, but most of the time we do, because we get more moment capacity out of the same reinforcement that way, if they are close to the edges. The remainder of the shear wall length, we provide the horizontal as well as the vertical shear reinforcement. Okay. The concentrated flexural reinforcement at the ends is confined. We have hoops around them. The rest of the way, we have, if it is a thin wall, we have one layer of horizontal and vertical distributed reinforcement. If it is two layers of steel, if it is a thicker wall, we have two layers of distributed horizontal and vertical shear reinforcement. Okay. Two curtains of reinforcement are required when vis-a-vis the required shear strength exceeds 2 square root of f sub c prime in our units. Okay. Now, 318.14 says if the height to length ratio of your wall is larger than or equal to 2, then you need two curtains of reinforcement irrespective of how much the shear is. Okay. Then for height to length ratio less than or equal to 2, where you are not exactly assured of flexural failure ahead of shear failure. If height to length ratio is less than or equal to 2, the vertical shear reinforcement ratio shall be at least equal to the horizontal shear reinforcement ratio. Okay, so for the shorter walls, all the way up to height to length ratio of 2, the vertical shear reinforcement shall not be any less than the horizontal shear reinforcement. Then, actually, for other walls, ACI 318 tells you if you need so much horizontal reinforcement, you shall also provide so much vertical reinforcement. But then for height to length ratio less than or equal to 2, the vertical shall not be any less than the horizontal. Finally, if the shear is very low, lower than 1 square root of f sub c prime in our units, then the horizontal reinforcement is really not shear reinforcement. It is more like flexion, and it's more like shrinkage and temperature reinforcement. Then we do not have to get hung up on the minimum of 0.25%. Then your minimum can come from section 14.3. We can go down to 0.2% or even lower, as given in chapter 14 on walls of ACI 318. In your case, it is section 11.6. Okay, so if the shear is very low, then the minimum of 0.25% can be reduced, can be relaxed. This is ACI 318.14 requirement. The requirement, this is commentary on the requirement that I showed you, that all walls that have height to length ratio larger than or equal to 2, irrespective of how much shear is imposed on the wall, shall have 2 layers of reinforcement. Okay. This is the commentary on that. The requirement for 2 layers of vertical reinforcement in more slender walls is to improve lateral stability of the compression zone under cyclic loads following yielding of vertical reinforcement in tension. Okay, so I think that's a pretty clear explanation. Now, the design of special shear walls for flexion and axial compression. Okay, here And only here I go back to ACI 31895. Up until now, the interesting thing is that in your case, it is not that ancient. Before BNBC 2020 went into effect, your code was BNBC 2006, and the ACI 318 edition that the concrete provisions of BNBC 2006 were based on was, to the best of my knowledge, ACI 31889, which is even older than 31895. So you have been designing by this old procedure up until now. I don't know how many people have already designed by BNBC 2020. So what I am showing you out of ACI 31895 is probably the way all of you have designed shear walls so far. That design procedure has or had major flaws and problems. It was the procedure was so bad that it kept the developer and the contractor on the west coast of the US, where the seismic hazard is high, from building shear walls in buildings that could really benefit for them. So the remedy came first not in ACI 318, but in the 1994 edition of the Uniform Building Code. 1994 UBC is where we introduced a different shear wall design procedure. Unfortunately, because of last minute changes we made, there was at least one major flaw that crept into the ACI, the 94 UBC procedure. We fixed it in 1997 UBC. The 1997 UBC shear wall design procedure was a huge improvement over what we had in 31895. So in 31899, the UBC 97 shear wall design procedure was brought in with a number of rather significant changes. Whenever something comes into ACI 318, that tends to happen. But it was basically the 1997 UBC shear wall design procedure that was incorporated in ACI 31899, as I said, with a couple of significant modifications. That procedure remained intact, okay? It was not further modified for a long time. It came in 31899, 31802, no change, 31808, no change, 31811, no change, but then in 31814, major changes that I'm trying to indicate to you, and then what I will not talk about today in 31819, further major changes, okay? So with that long background of where we have been and where we are, let us look at what we had in 31895, which I'm sure is the same as what we had in 31889, which is the way you have been designing shear walls up until now. Okay? So in this procedure, we are supposed to consider the factored axial load tributary to our shear wall. Factored axial load tributary to our shear wall. It is not the weight of the shear wall. It is all the load that is being dumped onto the shear wall by the floor slabs that are supported by the shear wall. We take the P sub u, divide by the gross cross-sectional area of the section. That gives us a uniform compression of P sub u over A sub g across the shear wall section. Okay. Then we take the factored overturning moment at the base. So this comes from analysis of the building containing the shear wall under code prescribed seismic forces, which are already strength level. Okay, so that gives us M sub u. We take the M sub u, divide by the gross moment of inertia of the shear wall section, multiply by half the length from the central line to the extremity. Okay. That gives us maximum compression on one face, maximum tension on the other face. If the combined compression, the compression due to P sub u plus the compression due to M sub u, if that adds up to more than 20% of F sub C prime, then we had to design our shear wall pretending that the web has disappeared, that it does not do anything for us anymore. So now we have to design the two boundary elements, the two columns at the ends, to carry the entire P sub u and the entire M sub u. So each of these boundary elements has to be designed to carry a compression equal to 1/2 of P sub u plus the overturning moment divided by the distance between the central lines of the boundary elements. Okay, so this column has to be designed for that compression. That column also has to be designed for that compression because earthquakes direction reverses. When the bending moment is in that direction, that column will be in compression under the overturning moment. Okay. Now, if the moment is so big that this column goes into tension, then we have a bigger problem because all the tension has to be carried by reinforcement. Concrete doesn't do anything for us. At that stage, we probably would try to change something, the proportions of the shear wall or something, because that is not a very tenable situation. Sometimes we would allow that, but most of the time, no. Anyway, the requirement that each boundary element be designed for that much of compression gave us very large boundary elements containing a whole lot of reinforcement. Okay, I will show you an example and you will see large boundary elements crowded with a lot of reinforcement. What the story I told you so far, I think, is bad enough. But now it gets much worse when I tell you that these compression bars that you need to carry 1/2 of P sub u plus M sub u divided by L sub W prime, all these bars must be tied and cross-tied like column bars. Remember, every other bar laterally supported by a corner of a tie or a cross tie. The maximum spacing center to center between any two supported bars, 14 inches, and the clear spacing between a supported bar and an unsupported bar, 6 inches. So all that transverse reinforcement has to be provided. In the case of a column, it is provided over the potential plastic hinge range. In the case of a shear wall, it had to be provided over the length of the shear wall, at the end of which the combined compression due to P sub u and M sub u goes down to 15% of F sub C prime. So 20% of F sub C prime triggers special confinement. Special confinement cannot be discontinued until P sub u over A sub G plus M sub u over I sub G times L sub W by 2 falls below 15% of F sub C prime. And that sometimes took 3, 4 stories, maybe 5 stories of a taller building. So this was a construction nightmare. The constructability was a huge issue. Could this even be done? But that was not the only problem. Something else even worse what was happening. When we crowd the boundary elements with that much of reinforcement, we are getting a shear wall with very high flexural strength. Okay, that should be obvious to everybody. Okay, we crowd the boundary elements with a whole lot of reinforcement. We have a shear wall that is very, very strong in flexion. This shear wall will attract a whole lot of shear force to itself in an earthquake situation. When we do the shear design of this shear wall, we do not consider that fact. Okay, you saw yourself. V sub u comes from analysis of the structure under code prescribed seismic forces. It doesn't even consider whether the wall is over strength or under strength or what. Okay, so we were making brittle shear failure of the shear was highly likely. So we were cramming a lot of reinforcement into the large boundary elements, thereby giving us an unconservative design, shear walls that could fail in shear, that were almost certain to fail in shear before they had a chance to fail in flexion. This is the example that we are talking about. We did it in the UBC days when we had seismic zones. This is seismic zone 4, which was the highest seismic zone in the UBC. You see I thought we changed the units and I still see 28 feet and 26. Yeah, anyway, you see the building, the shear walls are L-shaped shear walls with boundary elements as in the picture. The building is 20 stories tall. The beams are 20 by 22 inches. The columns are 20 by 20. The walls are 12 inches thick. The boundary elements, when we did our design, turned out to be 38 by 38 inches. 38 by 38. 960 millimeter by 960. Each with 36 number 11 bars. This is our number 11, which should be 35 millimeter diameter. So 35 millimeter diameter bars. Again, 38 by 38 boundary elements, each with 36 number 11 bars. Number 11 is 35 millimeter diameter. The 36 number 11 bars have to be tied and cross-tied like column bars. So we have 1, 2, 3, 4 cross ties in each orthogonal direction. 1 tie all around and 4 cross ties in each orthogonal direction. Okay. Now you tell me, first of all, placing the reinforcement is difficult. Having placed the reinforcement, concrete placement is not easy. And then, as I pointed out, the shear strength or shear failure aspect of it. We are building flexurally overstrong shear walls, which will almost certainly fail in shear before they can fail in flexure in an earthquake. So the change made in 94 UBC, which eventually came to 318.99, was that, and this is huge. This is so big that I cannot even tell you. And please make sure that you understand this. Okay. We said in 94 UBC that it does not make any sense to make this distinction between the boundary elements of the shear wall and the web of the shear wall, and to pretend that the web does not do anything for us when it comes to flexion and axial loads. The web which carries shear for us, in shear design we actually neglect the flanges. That same shear wall somehow is supposed not to do anything for us when it comes to flexion and axial load. This design procedure was a throwback to the days when shear walls used to be infill frames. And the infill actually used to get damaged in an earthquake. There was diagonal shear cracking leading to the failure of the infill, and the frame ended up doing seismic resisting. Okay? But those days are long behind us. Shear walls, for a long, long time, have been monolithic concrete construction. The columns at the end and the web are constructed at the same time. Anyway, so 94 UBC said, for the purposes of designing for flexion and axial load, a shear wall is no different from a column. The entire cross-section is effective, the flange as well as the web. So when we design a shear wall for flexure and axial load, it is the same as column design. We establish a P sub n, M sub n interaction diagram using the same computer programs that we utilize for columns. We go from the nominal interaction diagram to design interaction diagram by applying proper phi factors to the nominal strengths. And we make sure that all combinations of M sub u, B sub u coming from the design load combinations are within the design interaction diagram. So that's now our shear wall design. Okay? So design as if your shear wall is a column. That's pretty much what the first line is saying. And don't worry about slenderness effects and the fact that because a shear wall is a deep element, the strain distribution across the section may in fact not be linear. Don't worry about it. Still go with linear strain distribution. So don't worry about slenderness effects and don't worry about possible nonlinear strain distribution. Sorry. Okay, now some details. Effective flange width. If you have very wide flanges to your shear wall, does the entire wide flange work for you, or because of shear lag, do you have to discount the remote portions of the flange? And so effective flange width shall extend from the face of the web a distance equal to the smaller of half the distance to the adjacent wall, so you cannot obviously encroach on the flange of the adjacent wall. You can go halfway to the next wall, and so the smaller of 1/4 of the total height of the shear wall. 1/4 of the total height, or half the distance to the next wall. Total height. So if the height of your shear wall is 200 feet, you are talking about 50 feet overhanging flange width. So this effective flange width is so generous that we typically do not discount anything. If you have a physical flange, all of it is considered effective flange. That's what it amounts to. But this is the regulation in ACI 318. Now, do we need specially confined boundary elements at the ends? This is a very, very significant topic. Let me put it this way, explain it this way. I started the, maybe not started is not right. Anyway, I said in our discussion to introduce the current design method that there is no difference between a column and a shear wall when it comes to design for P&M. That is true, but not quite. There is a huge difference between a column and a shear wall. The difference is almost the entirety of a column cross-section has to be tightly confined. With the exception of a relatively thin cover, the entirety of a column cross-section has to be tightly confined. A shear wall section that may be 30 foot long are you going to tie and cross tie the entire 30 foot long cross section like it is a column cross section? That would be very expensive and time consuming, but much more importantly, much of that confinement won't do you any good. Because a shear wall has significant compression only over a small part of that 30 foot length. And where there is no significant compression, the confinement is not going to do you any good. It cannot do you any good. Okay, so UBC 94 said and ACI 318/99 said you shall confine those parts of a shear wall cross section that develop significant compression under the design earthquake. Okay, you shall specially confine those parts of a shear wall cross section that develop significant compression under the design earthquake of the code. The big question then became what is significant compression? How would you determine how much of the wall is in significant compression? And that's where UBC and 99 ACI differed. ACI 99, ACI 318/99 used calculated neutral axis depth as the trigger. In the UBC, we actually tried to compute that strain, and I wouldn't go back there. Okay, so how much of the shear wall cross section to confine? You can figure it out two ways: by section 962, which is called the displacement based approach, or 963, which I will call the conventional approach. It doesn't have a name in ACI 318. So you can figure out whether you need special confinement and how much special confinement you need using section 962 or 963, the displacement based approach or the conventional approach. Okay, the displacement-based approach 962 is not applicable to all walls. It is essentially applicable only to cantilever walls hinging at the base. This is my paraphrase of what 318 tells you, but that's what the code tells you. The method is applicable to cantilever shear walls hinging at the base, effectively continuous from the base of the structure to the top of the wall, designed to have a single critical section for flexion and axial loads. 318.14 has added that the displacement-based approach is applicable only to the high-rise wall height to length ratio larger than or equal to 2, the flexure-governed walls. Okay, this is the crux of the displacement-based approach. If the calculated neutral axis depth is larger than or equal to a critical neutral axis depth, which is the right-hand side of this inequality, then part of your shear wall cross-section is in significant compression. If the calculated neutral axis depth is larger than or equal to the critical neutral axis depth, you have significant compression over some part of a shear wall cross-section. Okay. L sub W is the total length of the shear wall. It is not only today, I think that was introduced earlier. Okay. H sub W is the total height. H sub W and L sub W are very basic. Never lose sight of them. Okay. That definition, those notations never change in 318. H sub W is the total height of the shear wall. L sub W is the total length from one extremity to the other. 600 obviously is a constant. Delta sub U is described as the design displacement, total lateral displacement expected from the design basis earthquake. That may or may not help you. So let me tell you about delta sub U. So you analyze your structure containing the shear wall that we are designing under code prescribed seismic forces. The design base shear of the code distributed along the height of the structure in the manner prescribed by the code. Delta sub U is the displacement at the top of your wall coming out of that analysis, amplified by C sub D for the structural system that you are utilizing for seismic resistance. Okay, so delta sub U is the displacement at the top of your shear wall obtained from analysis of the structure containing the shear wall under code prescribed seismic forces, but it is amplified by the deflection amplification factor C sub D for the structural system you are utilizing for seismic resistance. If it is a bearing wall system, C sub D is 2.5. If it is a building frame system, it is whatever value the table gives you. Okay. So that's delta sub U. Now in 318.14, in a very, very important change, this 1.5 was inserted in the denominator, which meant that many, many more walls will end up requiring special boundary elements, specially confined boundary elements. Okay. C exceeding the right-hand side means you need special confinement. So if you insert 1.5 in the denominator, you are making the right-hand side smaller, so it will be easier to exceed the right-hand side, so you will end up requiring special boundary elements in more and more walls. So this is a huge change in 318.14. the idea is up until 31814, we were trying to uh, design. I want to state in simple terms. We were designing our shear wall for the design earthquake displacements. ACI 31814 is telling us to design our shear wall for maximum considered earthquake displacements. And maximum considered earthquake is 1.5 times the design earthquake. That's where the 1.5 comes from. But anyway, I don't want to spend a lot of time. It's 31814. It will be a long time before you are asked to uh, uh, use that. But the reason I mention is you can see very plain and simple that it is a huge change that we introduced in 31814. The delta sub U over H for very rigid buildings will be a very small number. It cannot be taken any smaller than 007 as part of this package, or in 31814, it won't be taken any smaller than 005. The calculated neutral axis depth C, the notation just says distance from extreme compression fiber to neutral axis. That doesn't tell you anything. Corresponds to the largest neutral axis depth, and then there is commentary which is helpful. Anyway, let me tell you, this is extremely important what this calculated C is. Okay, how what it exactly is. So the first and basic thing is whether it's a column or a shear wall, the higher the axial load applied to it, the larger the neutral axis depth. Okay, the higher the axial load is compared to the bending moment, the larger the neutral axis depth. And in the extreme, if there is no moment, only axial load, then the neutral axis depth is infinity. You have uniform compression. Okay. Now, axial load on a shear wall will come from the designed load combinations, and there are only two seismic designed load combinations. We have seen them many times: 1.2 dead, 0.5 live, 0.2 snow, 1.0 E. The snow term is immaterial for you, and 0.9 dead plus 1.0 E. I have described that as the additive load combination, that as the counteractive load combination. Here, the gravity causes compression. The earthquake also causes compression. In the counteractive load combination, the gravity causes compression, but the earthquake now causes tension. So we use this load combination to calculate the lowest compression or the highest tension. We use this load combination to figure out the largest compression that can come on our shear wall. Okay, so the largest axial load which will give us the largest neutral axis depth will always invariably come from the additive seismic load combination. It simply cannot be otherwise. Okay, so that is this P sub U. To go with the P sub U, there is an M sub U. There is also a moment to go with that axial load. The important thing is we do not calculate our C for the combination of P sub U and M sub U. We don't. We figure out the nominal moment strength at the critical section at the base corresponding to the P sub U. When P sub U coming from the additive seismic load combination is acting on our shear wall. What is the nominal moment strength at the base of the shear wall section? We get that from the nominal load moment interaction diagram of the shear wall section. Okay. The neutral axis depth C must be computed at that location for the combination of P sub U and the corresponding M sub N of the critical shear wall section at the base. P sub U and M sub N of the critical section. Okay, it's very, very important to understand that that is the C we are talking about. If this C exceeds the critical neutral axis depth, then some part of the shear wall cross section has to be specially confined. Okay. Now, when special bounded elements are required by that criterion, our calculated C went beyond the threshold, then over what length of shear wall do we provide? Over what height of the shear wall do we provide special confinement? Obviously, we started at the base, but then where can we discontinue it? So the special confinement must continue for a height of the shear wall equal to the length of the shear wall. If it is a 20-foot long shear wall, the special confinement must extend at least 20 feet over the height, or the factored bending moment at the base divided by 4 times the factored shear at the base, or 1/4 of the moment to shear ratio at the base. Whichever of the two is the larger. Okay, so that gives you the vertical extent of the confinement. Now, as far as, so this is from the critical section up. Below the critical section, if this shear wall sits on another structural member, you shall go one development length of the, not one development length, you will go the same distance into that supporting structural member. So if the shear wall that we are talking about sits on another structural member of some kind, the special confinement shall extend into the supporting member by the same distance, L sub U, or 1/4 M sub U over B sub U. Or if the shear wall sits on a foundation or a footing, you shall go 12 inches into the footing. That is said somewhere else. We will come to that fairly soon. Okay, that is the vertical extent of the shear wall. Horizontally, how far do we go? We start obviously at the extremities of the shear wall, but then how far into the shear wall do we specially confine? And the answer is 1/2 of the calculated neutral axis depth, or the neutral axis depth minus 1/10 of the length of the shear wall, whichever again is the larger of the two. 1/2 of the neutral axis depth, or the neutral axis depth minus 1/10 of L sub W, whichever is the larger of the two. So the code gives you the vertical extent of the special confinement. It also gives you the horizontal extent of the special confinement. If it is a flange section, then the boundary element shall include the effective flange width that we talked about earlier, and shall extend at least 300 millimeters into the web. So the specially confined boundary zone shall be as shown hatched in the figure, 300 millimeters into the web. And I always consider the 300 millimeter from the flange web interface, not from the end of the section. So here it talks about, no, I told you wrong. So if it's not the same length, okay. So this is so the special confinement shall extend above the base by either the length of the shear wall or 1/4 of the moment to shear ratio at the base below the critical section. If the shear wall is sitting on another structural member, I said the same thing first, then I told you the wrong thing. Then the special confinement shall extend into the supporting structural member by one development length of the largest longitudinal bar, or if it is a foundation or footing, then 300 millimeters. No, I'll redo it. Let's take a break. I'll go back and tell you the whole thing one more time. Okay, let's take a 5-minute break. It's 32 after. We'll come back at 37 after. Okay, 37. Okay, let's start again. And I'll redo the extension below the critical section. I confused myself and therefore confused you. So let me redo it. Okay. Forget about what I said before the break. So the special confinement shall extend above the critical section by the larger of those two things, the length of the shear wall or 1/4 the moment to shear ratio at the base. Below the critical section, the special confinement shall extend by the same distance if the shear wall is sitting on another structural member. Okay. However, if our shear wall is sitting on a footing or foundation or mat of some kind, then the special confinement shall extend into the foundation by one development length of the largest longitudinal bar or 12 inches, whichever is the larger of the two. Okay, so if the shear wall is sitting on a foundation or a footing, the special confinement shall extend into the foundation or footing by one development length of the largest longitudinal bar or 12 inches, whichever is the larger of the two. Okay, some 2014 requirements. The thickness of the flexural compression zone. 318 says width. In my way of looking at it, we are talking about the wall thickness, including the thickness of the boundary element. Okay. So width of flexural compression zone over the length of the specially confined boundary zone shall be no less than 1/16 of the clear height of the shear wall. Clear height is from top of floor to underside of the ceiling. So in the specially confined boundary zone, in other words, wall thickness shall not be any less than 1/16 of the unsupported wall height. This is to prevent buckling of the shear walls, which had never been observed outside of a lab until it happened in the Christchurch, New Zealand earthquake and in the Chile earthquake. So we now added in 318.14 this minimum thickness requirement for the specially confined boundary zone. And then it says additionally, if the rest of it repeats the requirements for the displacement-based approach. But if the neutral axis depth is larger than or equal to 3/8 of L sub W, okay, if the neutral axis depth is larger than or equal to 3/8 of L sub W, that would indicate that your shear wall is not necessarily tension controlled. And in that case, the minimum thickness requirement over the specially confined boundary zone is 12 inches. Okay, the wall cannot be any thinner than 12 inches, 300 millimeters. So this requirement applies across the board over the specially confined boundary zone, wall thickness shall never be any less than 1/16 of the unsupported wall height. And then it says, if your wall may not be tension controlled, then there is an additional thickness requirement of 12 inches minimum. Okay, and this commentary explains a value of C larger than or equal to 3/8 of L sub W is used to define a wall critical section that is not tension controlled according to section such and such. Okay, and in that case, a minimum wall thickness of 300 millimeters is imposed to reduce the likelihood of lateral instability of the compression zone after spalling of covered concrete. Okay, we talked a lot about specially confined boundary zone. The configuration requirement comes from that section of ACI 318, that section of BNBC 2020. The maximum spacing limitations come from that section, and the minimum amount of transverse reinforcement comes from that section. Configuration requirements, I have two slides. Well, this slide that has a lot of stuff in it you can read, but this is the summary of what all that writing is saying. So specially confined boundary zone reinforcement. What are the configuration requirements? We have gone over this multiple times. Every other longitudinal bar shall be laterally supported by a corner of a tie or a cross tie. The maximum spacing center to center between any two supported bars, 14 inches, 350 millimeters. And the maximum clear spacing between a supported bar and an unsupported bar is 6 inches. Okay. The every other bar laterally supported and the 6-inch clear are required irrespective of anything. It doesn't even have to be a seismic confinement. The 350 millimeter maximum on H sub X is a seismic requirement. Okay, it is for special moment frame columns and special shear wall boundary elements. The X sub I in the picture is spacing between, it was center to center spacing of consecutive ties, the spacing between center lines of the ties or cross ties. 318-14, it became center to center spacing of consecutive supported bars. So there is a subtle difference between, it's minor, but again, it is a change. So X sub I is the spacing as you go around the perimeter, and the highest value of X sub I is H sub X, and that cannot exceed 350 millimeters. 318-14 has added that the maximum spacing cannot also exceed 2/3 of the boundary element thickness. So if it is a 12-inch thick boundary element, the maximum spacing cannot go beyond 8 inches. 8. It is not 14 inches anymore. So that is a pretty severe restriction that has been added by 318-14. Okay, so that is the configuration. The spacing of the transverse reinforcement, the vertical spacing of all that. This is one piece of transverse reinforcement, the tie and the cross ties together. Okay, what is the vertical spacing of that? Okay. Shall not exceed the smallest of. Okay, remember in the case of a column, it was 1/4 of the minimum plan dimension, 6 times the smallest longitudinal bar diameter, or this S sub 0, which is between 4 and 6 inches. As we go from a column to a special shear wall boundary element, there are only two relaxations. Special shear wall boundary element reinforcement is the same as a special moment frame column reinforcement, with two exceptions. One exception is that 1/4 of the minimum plane dimension in the case of columns is relaxed to 1/3 of the minimum plane dimension of the boundary element. Okay, 1/4 is relaxed to 1/3 of the minimum dimension of the boundary element. The second concession is that in the case of a column, the minimum cross-sectional area of transverse reinforcement shall be the larger value given by the two different formulas that you see here. In the case of a shear wall boundary element, we make the upper formula inoperative. We say that the upper formula does not count. The minimum cross-sectional area of transverse reinforcement shall come from the second formula. Now, this exemption has been rescinded in 318.14. So 318.14 onwards, even for special shear wall boundary elements, the minimum cross-sectional area of transverse reinforcement shall be the minimum of values given by the two different formulas. The quantities A sub G, A sub CH in that formula, what are they, is explained in this commentary paragraph and in this figure. Okay, I don't have any reason to go beyond that. Okay, this is a very useful summary of the entire displacement-based approach. Okay, so this is your trigger for special confinement. If the neutral axis depth is larger than or equal to the right-hand side, then you shall specially confine some part of your shear wall cross-section. Extent of the special confinement into the wall, larger of 1/2 of the neutral axis depth, or the neutral axis depth minus 1/10 of the length of the wall. Okay, as I said, the larger of, whichever is the larger of the two. Along the height of the shear wall, you shall specially confine either L sub W, a height equal to the length of the shear wall, or the factored bending moment at the base divided by 4 times the factored shear at the base, whichever again is the larger of the two. Okay, so this is the entire summary of the displacement-based approach. These are all 31808 section numbers on this figure. These are the BNBC 2020 section numbers. Same figure, nothing changes except the section numbers are BNBC section numbers. Okay, that takes us to the conventional approach. This is, okay, so in the conventional, remember, up until 31895, our threshold for requiring special confinement was the combined compressive stress due to P sub U and M sub U exceeding 20% of F sub C prime. And we could discontinue special confinement when that stress went below 15% of F sub C prime. In the conventional approach, we go back to those triggers. We go back to those triggers. However, this is extremely important. We do not go back to neglecting the contribution of the web to carrying P sub U and M sub U. We do not do that. Those days are gone. Those days are behind us. Even in the conventional approach, the entire shear wall cross-section remains effective in resisting P sub u and M sub u. Okay? So special bounded elements are required where the maximum extreme compressive stress is larger than 20% F sub C prime. We can discontinue that when the stress falls below 15% of F sub C prime, and stresses are calculated on factored forces using a linearly elastic model and cross section properties, as you have seen. Okay. So this is the summary of the conventional approach. If this trigger goes off, if the sum of the two exceeds 20% of F sub C prime, then we shall specially confine parts of our shear wall cross section. The horizontal extent of the special confinement is the same as in the displacement-based approach. Exactly the same. The extent of confinement into the shear wall is 1/2 of the neutral axis depth of the neutral axis depth minus 1/10 of the length of the shear wall, whichever is the larger of the two. So even in the conventional approach, we need to calculate neutral axis depth. Along the height of the shear wall, as I said, we are allowed to discontinue the special confinement when the combined compressive stress falls below 15% of F sub C prime. Okay? So this is the conventional approach. Now, what is a specially confined boundary element or boundary zone? As I said, it is basically a special moment frame column. Now, the first thing is special confinement doesn't require a thickened portion of the wall. We can have a specially confined rectangular wall. That is totally fine. The special confinement is in the detailing. We do not need a wall section at the end that is thicker than the remainder of the wall. Okay. The minimum cross-sectional area of the legs has to be larger than or equal to the value given by this equation. That's where we are at now. In 31814, whenever that is adopted in Bangladesh, it is going to be the larger amount given by the two formulas. The spacing, vertical spacing of all of that, as we saw, 1/3 of the minimum dimension of the boundary element, 6 times the longitudinal bar diameter, or the S sub 0, which is between 4 and 6 inches, whichever is the smallest of the three. Okay. The distributed reinforcement, the horizontal as well as vertical, minimum 1/4%. The spacing no more than the 400 and the 18 inches, 450 millimeters. Okay. The next thing SEI 318 goes into is so this is horizontal shear reinforcement. We have hooked them for development. From the face of the boundary element to the end of the hook, or if you want to be conservative, you take it from here to the end of the hook, has to be L sub DH for hooked bars, hooked bar development length, or L sub DT for headed longitudinal bars. So this horizontal shear reinforcement, for the horizontal shear reinforcement to carry shear for you, it has to be properly anchored. And the anchorage requires that we have either hooked bar development length beyond the face of the boundary element, or headed bar development length if we are using headed bars. Now let us say L sub dh comes only up to here, or L sub dt comes only that far. ACI 318 says even if that happens, bring the hooked bar to within 6 inches of the end. Okay, you bring it close to the end of the shear wall, keeping sufficient cover, but do not make this distance from the end of the hook to the end of the wall more than 6 inches. That is, in very basic terms, to grab as much concrete as you can with the horizontal bars. This is very crude common sense kind of a requirement. Okay, so go as far as you can into the boundary element, come within 6 inches of the end of the shear wall, not compromising the cover requirements. Now, in some cases, ACI 318 will allow you to terminate straight bars in the boundary element if you have room. So in that case, the straight bar development length, L sub d, has to be provided from here until the end of the bar. Now, this is allowed. Straight bar, straight shear bars ending in the boundary element is allowed, provided you have sufficient straight bar development length, also provided you satisfy this equation. Okay, here A sub B is the total cross-sectional area of the shear reinforcement, F sub y is the yield strength of the shear reinforcement, S is the spacing of the shear reinforcement, A sub sh is the total cross-sectional area of the confining reinforcement, F sub yt is the yield strength of the confining reinforcement, S is the spacing of the confining reinforcement. Okay, if you have sufficient length and that, then we are allowed termination of straight bars in the boundary element. Even then, you are asked to bring the bars within 6 inches of the end of the shear wall. Now, when your trigger doesn't go off, neutral axis depth is lower than the critical neutral axis depth, you do not need specially confined boundary zones. Even then, you shall provide what I'm going to call non-special confinement at the ends of your shear wall if the local reinforcement ratio exceeds our unit is 400 over f sub y, your unit is 2.8 over f sub y. So if the local reinforcement ratio exceeds 400 over f sub y, 2/3 of a percent for grade 60 reinforcement, then you shall provide non-special confinement. What is non-special confinement? The same configuration. Every other bar lateral is supported by a corner of a tie or a cross tie and so forth. Okay, configuration is the same. Spacing we will talk about in a second. The extent of the non-special confinement is the same as the extent of the special confinement. Okay, you go into the wall 1/2 of the neutral axis depth, or the neutral axis depth minus 1/10 of L sub W, whichever is the larger of the two. The spacing of the non-special confinement, this is where there is the difference between special confinement and non-special confinement. Special confinement, you are looking at a spacing of 3 or 4 inches. Here, it is 8 inches, 200 millimeter is the spacing of the transverse reinforcement. Okay. ACI 31814 will say the lesser of 8 inches or 8 times the bar diameter. So right now we have maximum spacing of 8 inches. 31814 will make it 8 inches or 8 bar diameter, whichever is the smaller of the two. To make it worse, ACI 31814 will say over the, so starting at the base, over the length of the shear wall or 1/4 of the moment to shear ratio at the base, whichever is the larger of the two, your transverse reinforcement spacing shall be 6 inches or 6 times the bar diameter, whichever is the smaller of the two. Okay. So this good old 8 inches you will enjoy for quite a long time, but here it is gone. It is now much more stringent and somewhat more complicated. What is this local reinforcement ratio that we are talking about, which exceeding 400 over f sub y will trigger non-special confinement? If you have distributed reinforcement, the reinforcement that we need for flexure and axial load, we decided to evenly distribute throughout the shear wall cross section. That we sometimes do for rectangular walls that are low rise. Then the local reinforcement ratio is simply the area of 2 bars divided by the spacing. Okay, as simple as that. But more typically, we would concentrate the flexural reinforcement near the ends, and then we would have distributed reinforcement. In those cases, we will, so this side we have an actual clear cover. On the other side, where the wall continues, we shall imagine the same cover. Okay, and then the local reinforcement ratio will be the total area of all the flexural bars divided by the area of the shaded section. Okay, the shaded part of the section. I think that's pretty clear cut. Okay, so the total flexural reinforcement area divided by the area of the section where it is placed, and in calculating that area, we imagine a cover this side which is the same as the cover on the other side. So that exceeding 400 over f sub y will trigger special confinement reinforcement. The non-special confinement reinforcement, the spacing of which is 800 millimeters or less. When we do not have special confinement or non-special confinement at the end, how do we anchor the shear reinforcement? So when, here I forgot, this should be 0.08 in your units. Our unit is 1 square root. So if shear is below 1 square root, you don't have to worry too much about anchorage. But if it is more than 1 square root, then you have to anchor the shear reinforcement in one of two ways. You will hook around a vertical bar, or you will install a U-stirrup around the vertical bars and then lap the shear bars with the U-stirrups. One way or the other, but you will have to anchor the horizontal shear reinforcement as long as the shear is larger than 1 square root of f sub c prime. Okay, then ACI 31814 has added two figures which I think are very useful. The difference between the two figures is here we have used the displacement-based approach. In the other figure, we have used the conventional approach. That does not make any difference. The main points of the figure that I want to emphasize to you that is not well understood is, so your calculations show that at the critical section you need special confinement. Okay. Special confinement shall be extended over the distance that we have discussed many times, and into the foundation it will be one development length of the largest longitudinal bar at 12 inches, whichever is the larger of the two. The question is, where special confinement drops off, we don't need it anymore. What then? Typically, at that section, we will still need quite a bit of compression reinforcement. So we will exceed the local reinforcement ratio, typically exceed 400 over F sub y. So we shall provide non-special confinement hoops at 18 spacing. Okay. When that isn't required anymore, the local reinforcement ratio drops below 400 over F sub y. Then it is not that we don't provide confinement as shown in the figure, but now we go to normal column confinement, the 14-inch ties, whatever is required by chapter 7. Okay, so this needs to be understood. So typically you have special confinement, and then we have non-special confinement, and then ordinary column detailing. That's what we have in a boundary element from the base to the top. This figure has not been converted to metric, nor has been this figure, but I hope you will excuse that. The only point I wanted to make is the point I made. Okay. Now, mechanical and welded splices of longitudinal reinforcement of bounded elements shall conform to sections such and such. That brings us to coupling beams, a significant subject. These are the beams between typically two shear walls, could be more than two, beams that are typically above window or door openings. The thing about coupled shear walls are the shears at the ends of the coupling beams add up to compression on one of the walls and tension on the other wall that is coupled. This tension compression couple resists a part of the overturning moment, leaving only the remainder of the overturning moment to be resisted by the shear walls themselves. So we can spare the shear walls from damage by sustaining damage in the coupling beams, which are much more easily repairable. So these are pretty popular. The detailing of coupling beams that are, what I want to say is ACI 318 only has special detailing requirements for coupling beams. Okay, there is no non-special detailing that is specified. So we are looking at special detailing, although it is not called that. It is part of the special shear wall section. So the requirements are if the clear span to total depth ratio, clear span L sub n to total depth H ratio is larger than or equal to 2, you detail your coupling beam as if it is a special moment frame beam. Okay, and you know those detailing requirements. So clear span to depth ratio larger than or equal to 2, you detail your coupling beam as a special moment frame beam. If the clear span to depth ratio exceeds 4, you may, but you do not have to use diagonal reinforcement in your coupling beams, and I'll show you what that diagonal reinforcement looks like. If the clear span to depth ratio exceeds, not exceeds, is smaller than 2. We talked about 4 here. We are now talking about really short and stocky beams. If the clear span to depth ratio is below 2, and at the same time, the shear in the coupling beam exceeds 4 square root of f sub c prime. Now you shall use diagonal reinforcement in your coupling beams. This is what diagonal reinforcement looks like. Each diagonal shall consist of at least 4 bars. You can have 40 bars, you cannot have 3, at least 4 bars. And those bars shall be tied and cross-tied like column bars. Okay, so you have intersecting diagonals. Those diagonals have to be individually confined. And then there are reinforcement requirements for the coupling beam itself. I wouldn't go into the details. The details are on this figure. It's way too much detail, but I want to show you that difficult as it is, this is done. This is in Honolulu, Hawaii, in the very early days, they constructed diagonally reinforced coupling beams. And Dick Levy, who was a prominent practitioner there in those days, he gave me this picture. It shows what you need to see, and you see that the coupling beam itself does not have a lot of confinement. Then I have 3 pictures from John Wallace of UC University of California, Los Angeles, that I think are very, very nice pictures. The diagonal reinforcement and the cage for the coupling beam itself. You see the span to depth ratio. This is a more slender. You see the diagonal, you see how much development length. You need a lot of room to develop these things. And then a very short stocky coupling beam. Okay, you see the diagonals, and you see the extent, the development length. So these are obviously real cages. Now up until 31805, the individual diagonals had to be confined. We had no choice. Starting with 31808, based on John Wallace's tests, we have provided a second alternative where instead of confining the individual diagonals, you can confine the entire coupling beam cross-section very tightly. Okay, so this is a very attractive alternative. Most people are doing this now because confining the diagonals was a pain in the neck. And this is, John has shown that this is as good as the other confinement. So in picture, these are also John's pictures, not mine. So this is what we had to do up to 31814, individually confined coupling, individually confined diagonal reinforcement. Okay, this is one diagonal, this is the other diagonal, and there is some additional reinforcement in the coupling beam. This is the 31808 solution. The individual diagonals are not confined, but the coupling beam cross-section is tightly confined, including the hairpins that go into the shear wall, into the coupling beam. Okay. Okay, that brings me to the last topic of the day, wall piers. So door and window openings in shear walls often lead to narrow vertical wall segments, many of which have been defined as wall piers in the IBC and in the UBC before it. Wall pier provisions were first, we tried to bring wall pier provisions into ACI 318 somehow. It took a long time until it happened in 318.11. So for you, this is not in not in the code, but this is pretty important. So the dimensions defining wall piers are given. So the wall piers, everything in ACI 318, is defined in chapter 2, section 2.2, and wall piers are no exception. So we have added this figure, and I would like to like you to take a look, and also I want to tell you that I included this, although this is 318.11 stuff, that because it is extremely important in my opinion. When you have openings in your walls, and in the US, parts of the United States, quite popular is what is called tilt-up construction. You cast the walls on the slab on grade. Assume the slab behind the wall. You actually cast the wall on that slab and then tilt the wall up after it has hardened. Okay, you tilt it up, make it vertical. Initially, it started out as tilt-up walls, but then people started cutting openings for obvious reasons. And now, sometimes it's hard to tell whether these are tilt-up walls or tilt-up frames. The problem is that those segments between the openings, or this segment between the opening and the edge, those are particularly vulnerable to shear failure in an earthquake. We saw that in earthquake after earthquake. Those elements failed in shear simply because they are the contractor and the engineer do not treat them definitely as columns, so they do not have confinement. And many times, because these walls are thin, they would put only one layer of horizontal and vertical reinforcement. So there is absolutely no confinement. And the shear carrying capacity is very low. So this was a huge problem until UBC defined these wall piers and required that we design them to fail in flexure before they can fail in shear. Okay? So this is the brief history. For one of those segments to be defined as a wall pier, the height to length ratio has to be larger than or equal to 2. So the height of the wall segment to the length ratio has to be larger than or equal to 2. And then the length to thickness ratio has to be between 2.5 and 6. So both have to be true for you to have a wall pier. Height to length ratio larger than or equal to 2, and the length to thickness ratio between 2.5 and 6. Okay, shear failures of wall piers have been observed in previous earthquake. Yeah, this I think we can. Okay, the main thing I want to convey to you is summarized in this table that is in the commentary to ACI 318, table R21.9.1. Okay. So if the height to length ratio of your wall segment is less than 2, then you cannot have a wall pier. Then you have wall, and you reinforce them as a wall, and you should not get into any trouble. For you to have wall piers, height to length ratio has to be larger than or equal to 2. Okay, if that is your case, and the length to thickness ratio, the thickness was denoted by H in the figure, that has become B sub W in the table. At one point ACI switched, and I did not think of changing the figure. Okay, we are talking about the same thing. If the length to thickness ratio of the wall segment is less than or equal to 2.5, then it is a column, and you must reinforce it as a column. This is very, very important. If the height to length ratio of the wall segment is below or even equal to 2.5, you are looking at a column, and you must reinforce the segment as a column, not as a wall. If the height to length ratio is more than 6, then you have a wall, and you can reinforce the wall segment as a wall. Should not have any qualms about it. That shouldn't give you any problems. However, in between, if the height to length ratio is between 2.5 and 6, now you have a genuine wall pier as defined in 318. Now you will have to reinforce it to prevent shear failure preceding flexural failure. And we give you those requirements in this section 2198. The final thing, this was never in the UBC or the IBC, but we have added this in 318. So this is a wall pier at an edge of a shear wall, a wall pier at an edge of a shear wall. Okay, if the earthquake direction is as shown in the figure, direction of earthquake forces, then compression diagonals will form as shown in the picture in the wall pier or in the wall segment. To equilibrate that compression, we will have tension at the top of the opening, and we must provide reinforcement to carry that tension. When the earthquake direction reverses, there will be compression, diagonal compression in the wall pier in this direction now, as shown in the picture. Now there will be tension below the opening, and we must have tension reinforcement to resist that tension. So because earthquake direction is reversible, that tells us that we must have reinforcement above the opening and below the opening. And that is a requirement of ACI 318. Okay, that brings this segment to a close. We are almost precisely on time, 4 or 5 minutes ahead of time. So I am definitely open to questions now. And we will do it the same way. Both you will read the questions to me, and I will try to answer. Okay,
Okay, Dr. Ghose. So I'll start from the very beginning. Is it possible to have a boundary element column having the same width of the shear wall flange section?
I don't even know what that means. You either have a flange or a column, or you don't have anything. You just have a rectangular wall. What does it mean? A column the same width as the flange?
I think he's talking about the width of boundary element. So is it possible to have a boundary element width that covers the shear wall flange section? I don't know.
That's what I don't understand. As I explained before, if you need a specially confined boundary zone, let me go to that figure. In a flange section, that's what a specially confined boundary zone looks like. Okay, you may have to go more than 300 millimeters if you need it, but the entire effective flange width will be part of the confined boundary zone. You have to specially confine it. So hopefully that answers your question. I don't quite understand what you are asking, but this is what it looks like. Specially confined boundary zone for a flanged section.
Okay. Which approach is better, displacement-based approach or conventional approach?
I don't know. I wouldn't know what better means. The displacement-based approach is, I would say, is probably a little more sophisticated. In that sense, it may be preferable, but I would emphasize that it is applicable only to cantilever walls hinging at the base. There are, and starting with 318/14, it will be applicable only to walls with height to length ratio larger than or equal to 2. So there are conditions of applicability. You cannot apply it to any wall, whereas the conventional approach applies to any wall.
Okay. Go. This question I didn't understand.
Hmm.
I mean, like, okay, I'll read it out to you. Maybe you will also feel the same thing. If significant compression is developed by a beam resting at the midpoint along the length of the shear wall, should we design that point by providing confinement reinforcement like column, or should we consider the stress to be distributed throughout the wall length? So is the beam resting like over the wall?
I like you. I do not understand it.
Yeah, I've never seen this case ever, basically. Like, yeah, I
I
didn't understand this question when I read the first time also.
no, I don't understand.
Okay, shear wall which is 20 feet wide.
Hmm.
In that shear wall, transverse reinforcement might require lapping. Where should we place the lapping? And tell us about the lapping procedure.
I read that again.
A shear wall which is 20 feet wide.
Hmm.
In that shear wall, transverse reinforcement might require lapping. Where should we place the lapping? And tell us about the lapping procedure.
I think that transverse reinforcement, he must mean the horizontal shear reinforcement.
Yeah. That one.
Okay,
Not the.
so that, yeah, if that requires lapping, you just lap them somewhere near the middle. And the only thing with typical, not typically, always lap splice. I've never seen anything other than lap splice on the horizontal bars. And the only thing is you will stagger them. You will not lap them on at the same location on consecutive bars. So that's it. Somewhere near the middle or just to one side of the middle and lap them. I mean stagger them.
Again, something that has been discussed before.
Mhm.
If we place a shear wall in the first two floors of a 5-storied building
Mhm.
and this continues to other top floors,
Mhm.
does it lead to irregularity?
Does this need to irregularity? That
Does
you
does
have to
this lead
figure.
to?
Yeah, that you have to figure out by the criteria we discussed, the tables of vertical irregularities. So check them, and if you do fall under them, yes. If no, then no.
If someone put closed stirrups, closed stirrups, uh, I'll read out the question, Dr. Ghosh, and then figure
Mm,
out what it means. So
mm.
if someone put closed stirrups in some column in a floor without any reason, and put general column detailing in some column on the same floor, does it attract more load? So if stirrups are closely spaced in a column, does that portion attract more load? I think that is what he's asking.
If the stirrups are more closely spaced in some region than in other regions, does that attract more load to the closely spaced region? I see. Interesting question.
I believe that is what he's asking.
Yeah, I honestly don't know. I don't think there is any significant difference because you know, whether loads are attracted depends on the stiffness. Does the close column spacing makes the portion stiffer? I honestly don't know. At least we don't consider in stiffness calculation. So I honest answer is I do not know. Maybe a little bit, but I don't think it is a significant difference. I don't think.
Okay. So moving on.
We do it the other way. We provide the special confinement where the stresses are high. We already know, like at the bases and things like that. So I don't know that this question really arises in design.
Right, right. If the boundary elements they come large enough that they overlap each other, does this ever happen, Dr. Ghosh?
Say that again.
If
Oh,
the,
the bounded elements at the two ends overlap.
yeah, they overlap each other.
Yeah.
What is the best solution? Increase the thickness of shear wall or increase the length of shear wall?
If the bounded elements overlap, then you will have to confine the entire length of the wall. That's what it means. If you can live with that, fine. If you cannot, then you probably need more shear walls in your building. So
Right.
I don't know. I don't know that it is a disaster. If that happens, you just have to confine the entire length of the wall. It's very uncommon.
Is it necessary to provide a beam at the top of the shear wall?
What is this preoccupation with beams? I don't understand. I you almost never put a beam on top of a shear wall. Why would you? So typically you will have shear walls and you will have framing outside of the shear walls. So the framing will have beams and columns. The shear wall will go up as far as it needs to. If it is discontinued, then the typically where there was a shear wall, you will now probably have two columns going up. Things like, yeah, I don't know. Why would you put a beam on top of a shear wall? I don't. I cannot see what the questioner is visualizing. I
Yeah, the other question was something else only. Even I am not understanding. So are they talking like that the shear wall is bounded by beams and columns? Are they looking at it like that? I don't know.
yeah, we definitely do not provide a beam-like element at every level within the shear wall. We do not. Okay, that is an unqualified answer. That would be a detailing nightmare. Okay, and there is no reason for us to do it. At the very top, if the shear wall is discontinued, do you build a beam at the top? That may happen. I don't know. That depends. It all depends on what you are trying to do, what the rest of your framing is. But I think this is the best answer I can give you. That along the height of the wall at the different floor levels, you never try to build a beam inside the shear wall. Never. At the very top, if the shear wall is discontinued before the rest of the framing, at the very top, whether you want to build a beam, that the answer is maybe. Yeah, I wouldn't know without looking at a particular situation.
Okay, moving on. What do you mean by height of shear wall? Total height or floor height?
I don't know how much clearer or more
Yeah, I
emphatic
think these questions were asked before, Dr. Ghosh, and
Yeah, but
then
I would like to say again, I mean, I have said literally 100 times or more. H sub W, if you see that notation, it is the total height of the shear wall, total height. For story height, I do not know that we have a standard notation. Somehow in either 318 or AC7, I don't think it is a standard notation. We have used H sub S, things like that, but it is never H sub W. H sub W is the total height of the wall. And the only time we use story height is in drift check. Okay? So in the design of a shear wall, I do not even know where you would need the story height. I just don't know. We use H sub W, which is the total height of the shear wall.
okay. So I will move to room 2. If the beam width is greater than shear wall width, uh, then how the beam rebar will be inserted into shear wall?
Mhm. Yeah, somehow there is a preoccupation with beams. Let me see if I can. Maybe I'm not catching on to something. I don't know. When everybody is asking the same thing, there has to be So this beam is coming into the shear wall. What is the question?
If the beam width is greater than the shear wall width, then
I
how
see.
the beam rebar will be inserted, will be continued to shear wall, into the shear wall.
I see. I see. Yeah, I do not know that I can give you a generalized answer. The beam bars have to be fully developed, and you could do that by I don't beams wider than the shear wall. Okay. Let me think about this. Now that I understand the question, yeah, I will see if I can provide some kind of an answer or detailing or something. Okay.
Yeah, rest of the questions are very fundamental here. So I think if they go over the webinar once more, one
Yeah.
recording once more, yeah. So
If you have bounded elements as in this picture, I don't think that you should have any problem with the beam bars, with developing the beam bars. If you don't have bounded elements, I can see that you have a relevant question, and I do not have an offhand answer. Have to think or see if somebody like CRSI has a detail or something. I don't. Yeah, I can't answer it offhand. Okay, so we ran out of questions for once.
no, there is like couple of questions, like, but
Yeah.
to answer those questions so many times,
Okay.
I hate to bring it again and again. But for strengthening an existing OMF building with BNBC 2020, if the code requires special moment frame now, then how could we comply the code requirement, and what should be the R value?
Read that again.
For strengthening of an existing OMF building, ordinary moment frame building, with BNBC 2020, if the code requires special moment frame, then how should we comply the code requirement, and what should be the R value?
So yeah, so I I understand what you are asking, but the code will never require special moment frame. The code will require how should I say? You can approach it two ways, as I once said. You can make the building much stiffer by building shear walls inside the building, or by providing bracing, and then you do not have to provide ductility, which you don't have. Or you can try to provide ductility. Now, obviously, you will not comply with the special moment frame requirements, but you do that by wrapping from the outside. There are techniques, or you can do jacketing. You can build columns around the existing column in which you have ductile detailing built in. So there are ways of approaching it. The code will never say you have to have special moment frames. The code will require either ductility or stiffness. Stiffness can be provided by building shear walls or bracing. That is typically, not typically, almost always the cheaper solution. Or you can try to give the moment frame ductility after the fact, which will require, as I said, either wrapping or jacketing or things like that, which are very expensive solutions. So, yeah, there is no cheap or easy solution.
So can we use coupling beams in building frame system to connect two separate shear walls?
It has nothing to do with building frame system. The coupled shear wall will be treated as a shear wall. And building frame system would mean that you have 100% gravity force resisting moment frames to go together with this coupled shear wall that will have to resist 100% of the lateral forces. Okay, so the coupled shear wall will take the place of an isolated shear wall in a building frame system. You can use it, but only in conjunction with 100% gravity force resisting moment frames.
If I choose dual system
Mhm.
that comprises of intermediate moment resting frame with special or
Shear walls.
ordinary shear wall,
Mhm.
and the seismic design category is D, how
Mhm.
should we detail the frames?
What's the question again? The last part I didn't quite catch.
If I choose dual system comprising of intermediate moment resting frame with
Yeah.
special or ordinary shear wall,
Yeah.
and the seismic design category is D,
Mm-hmm.
how should we detail frames and frames and shear wall? Should we follow special detailing for frames and shear wall?
Read that one more time.
If I choose dual system comprising of intermediate moment frames
Mm.
with special or ordinary shear wall,
Mm-hmm. Mm-hmm.
and the seismic design category is D,
Mm-hmm.
how should we detail frames and shear wall? Should we follow special detailing for frames and shear wall?
So if I I I don't know why there is a question here. So you are in this part of the table. You have intermediate moment frames. If you have chosen to use ordinary shear walls, you will do ordinary detailing for the shear wall and your R value will be 5.5. Okay. If you want to use an R value of 6.5, then you have to have special detailing for the shear walls. Then you have to have special shear walls. It is as simple as that. I don't know that there is any confusion here. Okay. So your walls, your frames are intermediate moment frames, no question. You said it yourself. So if you want to do ordinary detailing for the shear walls, your R value is 5.5. If you are prepared to do special detailing for the shear walls, your R value is 6.5. And I can tell you that this is much, much a cheaper solution by far. Okay. There is no reason for anyone to use special detailing in design category B. It never pays.
No, it's not B, it's D, as in dog.
If it is D, then you are not even allowed this option.
Yeah, you have to go for special shear walls.
Not permitted. Yeah, this part of the table you should look at. I was thinking B. In D, that is not an option. Okay, and even in D, you have a height limit of 15 meters. How much is 15 meters? 50 feet? I don't know. 60 feet, I think. Whatever. So in design category D, that is not a good system. This is your system for design category D. This is allowed subject to a severe height limit. Yeah, this turned out to be a good question. I didn't, particularly point at the height limits, but yeah, this
I
you
think
can,
you did. You did actually point out.
less, yeah, anyway, this you cannot use in design category D, period. It's not permitted.
So in a dual system, how we will calculate that the columns can take 25% of shear?
You don't. So dual system, you need to do two separate analysis. One analysis is the shear walls and the frames together. This is called the interactive analysis. The shear walls and the frames. Typically, you provide rigid links in between to indicate the diaphragm coupling, and you analyze under the code prescribed seismic forces. And then you do a second analysis of the frames only under 1/4 of the design lateral forces. The second analysis will give you the required strengths for the columns in the lower levels of the building, because the interactive analysis will show that very little shear develops in the columns. So the shear strength of the columns will come from the second analysis. You don't, the thinking that you have, you calculate something. What was the question? How do you calculate?
25% of the shear. How do you calculate that columns can take 25% of the
Yeah,
shear?
so you don't calculate that. You do this second analysis, and that gives you the basis for the design of the columns in the lower levels of your building.
Dr. Ghosh, we'll take the last question.
Hmm.
Is it mandatory in dual systems for the shear wall to calculate 100 to carry 100% of lateral loads?
No, no, no. It's only in building frame systems, not in dual systems. Absolutely not. No, then if that were mandatory, then there would be no meaning to very little meaning to the system.
Right.
Yeah.
I think we answered most of the questions
Okay.
that are relevant, and the other questions are very, very fundamental. Like you can
Okay.
go over the webinar once more and probably watch the recording.
Okay.
Yeah, Dr. Ghosh, were you saying something?
No, no, no.
Yeah.
Okay. Good.
So yeah, thanks for joining today's webinar. And tomorrow we'll have another seismic session.
Yeah.
And yeah, and I will turn on the feedback portion and turn on the quiz again. Any questions related to quiz and attendance sent to support. I repeat, support at prpportal.org. I saw a couple of comments, couldn't get a time to answer them. They sent it to some other email ID. Don't send it there. Send it to support at prpportal.org. You will get replied. And thank you once again for joining in huge numbers. Thanks, Dr. Ghosh, for this wonderful presentation. And we'll see you tomorrow.
Thank you. Yeah. See everybody tomorrow.